Hey everyone, I hope we are live.
We sure are.
So, welcome to our live lesson on how to enhance image resolution with GANs. Firstly, I would like to thank everyone for their participation. I am Ritik, a machine learning engineer here at PyImageSearch, and I am joined by two colleagues of mine, Aurithro and Dev. Say hello, guys.
Hi everyone.
Guys.
And this lesson is is going to include a little bit of theory, some code, and some explanation. But what we want from all of you is interaction. The more you interact, the more you ask questions, doubts, any ideas if you have, we want you to put them in the chat and share them with us. We'll be keeping an eye on the chat live as we go along so that we can talk to you in real time. So do not forget to, if even if you have a small iota of doubt, put it in the chat and don't wait for afterwards so that we can talk in real time. And now, before we actually go into the live lesson, we do have something for you. This is a little sneak peek of what is going to come afterwards. But if you're interested in deep learning, computer vision, we are giving a 25% off on PyImageSearch University and all of our products exclusively for this live lesson. So if you are interested in deep learning and computer vision, and if you want to enhance your career as well as enhance the image resolutions, so you can avail the discount of 25% by scanning these QR codes that you have on the screen. We'll talk about university and all products in details when we finish the live lesson and after you have gone through generative adversarial networks. But I just wanted to share these two QR codes with you, and I will also be putting them into the chat for you to access the links. So go ahead and take these, scan these QR codes if you want to. And just a word to the wise, they will be available for a limited time. So for a couple of hours more after this live lesson. So if you like sleep on it, or if you come back, day after or maybe next week, it probably won't be good. So now is the time if you are interested and if you want to do it. And now I will give it up to Auditro, who is going to walk us through the topics he has planned for us.
Great. So thanks for the wonderful introduction, Ritvik. Hi everyone. I am Auditro Roy Goshtipati. I am a deep learning associate at PyImageSearch. And what do I say? I just love generative adversarial neural networks. So does my colleagues here, Ritvik and Dev. So what we are going to go ahead with is an application of GAN. But before applying GANs, I just wanted to cover a little bit about what GANs are, how are they necessary, how are they creating an impact in the day-to-day world, and also a little theory which includes a little bit of maths, which might be overwhelming for some of y'all who are just beginning with GANs. But I assure you that we are going to discuss it as we do with our peers, we do with our buddies. And any doubts, as Ritvik said, any doubts, please write to us in the comments. We are keeping a keen eye on the chat, and we will come back to you in that moment, in that instant. So what are GANs? GANs are generative adversarial neural networks. So there are the three terms including in the entire thing. So why generative? Because we have something called as a generator inside of the GAN, which generates stuffs, right? And what does it generate? Why is it necessary? We'll come to that later. What is adversary? Adversary is somewhere where there are two enemies fighting against each other. Who is the enemy to generator, you might ask? The discriminator. So how are they enemies? We'll come to that later too. And neural networks? Turns out that generators and discriminators are neural networks. Hence the name generative adversarial neural network. Now let's step back. What do we mean by a generator? So as it turns out, we have a random noise which we symbolize as the letter Z. And from random noise, the generator generates images. Let's say images, it might be any data distribution or any data, maybe audio, maybe video, maybe text. But let's say, for example, we take images. And these are written as fake images, right? So the generator or the artist, as we call it, creates images which are fake, and they try to generate like as close images as to the real images that it has to fake too. So Dev, Ritvik, am I making a little bit of sense?
Yes, probably your voice is a little bit low. So if you could, come closer.
Okay, is it better now?
Yes, I think
Yeah,
so.
it is. It is.
Cool. So I'm sorry about the audio issues. So now that my voice is loud and clear, did I make sense of what the generator has to do? Like the task of the generator, just the generator. What does it do?
Yes.
It takes random noise. It generates fake images. And why are they called fake images? Because they're not the real ones, and they have to be as close as they can get to the real images.
Yeah.
Now the
Just
discriminator, yeah, Dave, go ahead.
no, sorry. Go ahead. I was just saying, just to add to that, they just like it's not like they have to be exactly the copy of the real images.
Right,
They just
right.
have to look like they belong with the real images. So that's a little thing to just hold on to.
Right. So,
So
and
hold
what
on to
does
that.
the Mhm.
Let me get that straight. So that means that the generated images will lie in the same distribution as the data for the discriminator, but the 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 thing to maximize is to make the generator so robust and so powerful that it can understand where whatever fake data it has to generate. Is that what you're talking about, Dev?
Yeah, but like if for our viewers who are like new to these words like distribution and absolute, like who are just like stepping into the world of new like deep learning, just think of it. Take the MNIST dataset for example. These are like the handwritten digits, right? They're
Right.
black and white images. So when we are seeing distribution, imagine that it's like those images, those handwritten data digits are like are like people, and they're living inside their own country. That's a land that only belongs to them, and our
Mhm.
generator here has to create what a handwritten digit such that it passes off as someone who belongs to that country. So
Right.
just
Right.
that anecdote helpful.
Yeah, it was. It
Okay.
was.
Okay. Before we go ahead, guys, with the explanation, so I'm
Mhm.
getting a lot of questions about whether this video will be recorded on YouTube. So yes, after this session ends, you will find this video on YouTube. There are a lot of implementation questions, some about batch normalization layer and how it takes up a lot of memory, and whether we talk about data preparation. Yes, we do. We talk about the code. We talk about the data preparation. There's a question about whether we talk about prepared datasets like MNIST or CFAR10. I think that is not applicable to this particular scenario because you need a very specialized dataset, as Orithro will be talking about. You cannot use MNIST or CFAR10. And there's also another very important question, which is about the generated images come from random noise. So how is it able to generate the fake data every time from random noise? And I think we'll be covering this as well.
Yeah. So let's take that question and then move ahead, because that question is like the stepping stone for my next part, which is the discriminator. So
Right.
stepping back, random noise generator generating fake image. We are up with
Mhm.
that. Now, what the discriminator does is it is called the art critique. So it criticizes the fake images and compares them to real images. So the discriminator has only one thing to do. It has to identify whether the fake images are fake images and also whether the real images are real images. That is all. And and think about it. The generator has a big task at hand. It has to fake an image so that the discriminator gets fooled to pass it or let it pass as a real image. And the discriminator is just a art critic. It understands, it gets real images, it says okay, they're good to go, they're authentic. It gets fake images, it says no, they are not. and they don't let it pass, and the discriminator does not let it pass. But the generator takes that signal from the discriminator and grows or iterates and trains itself so that it is able to let the fake image pass as a real image and fool the discriminator. So that is the two these this is why we call it as an adversary, because they are fighting against each other. The generator wants to create good fake images so that the discriminator gets fooled, and the discriminator on the other hand trains itself so that it can understand what the generator is trying to do and stops it from doing that. So both have two counterintuitive things to do, and in that process the generator gives us very real like images but still are fake. Does that make sense? Does that
So
how does that
so
make
it's like a seesaw. You
exactly
it
exactly like a
always
seesaw?
the either side always goes up or down, and
Exactly, they're just
your
fighting
job
against
is
each other.
to balance it out.
Right, and this is a very good point, Ritvik. Just before moving out to the loss functions and all that stuff, it's a seesaw, and we as deep learning engineers who will understand how to train a GAN and GAN stabilities, and we'll talk about them a little more. We need to understand that we need to stabilize that seesaw to that point where the generator is good enough and the discriminator is also good enough uh, to pass a real like image. That if the generator is doing fabulously and the discriminator is doing nothing, we have what is called as a mode collapse, where we are getting random images from the generator which is not even close to what the real distribution looks like. The discriminator is just letting it pass, like it's a very lazy art critic, does not even pay heed to what the features are, right? But on the other hand, if the discriminator gets too powerful, then it will understand each and every fake image, and the generator is not going to do that. Like the generator will not be capable enough to provide good images. It's just going to lose hope and say, okay, the discriminator is anyway going to, prohibit my images. I'm not going to submit to that gallery, right? Does that make sense? So in that sense, they are going to stabilize to a state. The seesaw is going to stabilize to a state where the generator generates and the discriminator discriminates, but they are in unison and they're not fighting anymore against each other. So that stability is where we what we called as an inflection point, which we'll come to later. And
Yeah, I think
yeah.
about that inflection point,
Mhm.
Ajay has a question
Right.
saying at point 5 it toggles, meaning the generator toggles, and how do
Mhm.
we avoid that? And I think the main part is the main motto is, from what I gather from Orchard,
Right.
is to understand when it reaches that point and to stop it beforehand, so that our generator is good enough. It's not overfitted, but it's good enough
Good
and
enough.
can generate real like images. Is that
Yeah,
is that
and
something?
that is
Yeah.
absolutely what we do. And just to spoiler alert, GANs are terribly difficult to train. I'll say that loud and clear. It's very difficult to be trained. So we need to, babysit a model. I'm using the term babysit, which we quite frankly use at PyImageSearch, because we just sit and see the losses go down or maybe not go down and see what we can do. We revert to different checkpoints. We store the checkpoints and do all kind of stuff. So
Mhm.
you need to understand that it's not you just can't see a generator perform nicely. The loss needs to stabilize, and also it can go up. You can't just look at a loss landscape, for that matter, or a loss graph, and decide that the generator is doing good or the discriminator is doing good. You have got to have some kind of validation going on, which we will come to later, like generate images after every 10 epochs, right? And you can see from your own intuitions, or use a FID loss or some loss which gets a validation of how the generator is
So
working.
what is an FID loss?
Will not go into too much of depths. I'm sorry, I just spoke off because I love GANs. Um, we'll not go into that loss, or maybe a metric. But we do cover about FIDs. We do cover about generative adversarial neural networks in depth in our free tutorial. So I would really want everybody to go there and look at our blog posts, gather our code. If there are university members out here, they have all the zips, all the collab notebooks available. So coming to that point where Ritvik says about the QR codes, I would really, really want everybody to join in, because this is like the opportune moment for anybody looking into getting into university or our products, any of our products, because you get like proper code implementations right off the bat with videos as well as blog posts. But now if you don't do that, you'll just get free tutorials which are blog posts, and they do make sense, but they are not as cool as us talking to you on a video, or maybe a collab notebook which you can run off the bat. So just chiming on that part again. So yeah, that's about it from my end, the generative adversarial neural network architecture. So Dev, do you have anything else to cover on GANs? Maybe we'll move on to the loss part a little later.
It's okay. Let's move on there. We'll
Mhm. Right.
So there's a question
Okay.
from Louis who says,
Right.
so there is not a guaranteed convergence. And Prabhav, I see your question as well about relevant papers for GANs. And
Mhm.
like these two tutorials about super resolution GAN and ESRGAN are from papers. We'll talk about these papers as well. But it's great that you know about WGAN by Martin. It's one of the great papers as well. So we covered a fair bit of GAN at PyImageSearch, so keep an eye out there. And
Yep.
so Dev, you want to talk about Louis' question about there is not being a guaranteed convergence?
I don't think, or to correct me on this. Correct me on this if
Mm-hmm.
I'm wrong. I don't think. I mean, it's not about convergence. It's the fact that the generator is going to learn, right? It is going
Mm-hmm.
to learn and learn, and it's about you validating the output that you see
Mm-hmm.
after each after certain epochs. Like you yourself are seeing the grid or something, that is the outputs that are getting rolled, and you yourself are deciding by yourself that the images are getting better. Right.
Right.
And obviously, if you do see the loss going haywire, then that is something that is obviously you don't want that. So, Orito, do you want to add onto that?
I do. So this does I would say that Lewis is right. It's not always about the convergence, because there is no guarantee that a generator converges, because it's not as simple as an image classification task, right? The task is that two people or two neural networks are working against each other. And Dave, I have seen that the loss can go haywire, but the generator provides good images. So I am not really sure how to answer that. But you have to understand that the GANs are terribly difficult to train. You have got to validate. That is good. Like what they've said, it's good that you validate your errors, or maybe the generations as you go. But I'm also in on Team Lewis, saying that it's not only about convergence, and there is no guarantee that it converges, but you need to validate as you go along. So moving ahead, we have spent a lot of time on GANs, and it just shows how excited we are on GANs. So next up is the crux of GAN, right? We call it a min-max game. The loss, in essence, is two terms. The first term is this. That is, let's bring out our laser pointer. This is where we call. Okay, so before we go into the loss, I just want to highlight some of the symbols in the loss that we are going to talk about. So E stands for expectation. Expectation can be thought of in a layman's term as mean, or reduced mean that we do in our deep learning projects, right? You want one scalar as a loss which backpropagates. So this is kind of one scalar that you're going to reduce it to. This, like x tilde p of data x, stands for x is sampled from a probability distribution of the original data. So this is real data, the distribution that we are talking about from real images. So these are the real images. The distribution of real images is p of data. And we sample some x, like we sample some images from the real data that we have, right? And having this, like having the sampled real images, we send it to the discriminator, right? And think about it, real is 1 and fake is 0. So the discriminator, upon getting real images, should give me what, Devjyoti or Ritvik?
Real.
Real, exactly.
Do
So
I win anything, Orito?
I don't know. You
That's
just
right.
have my good regards. So with X being sampled from real data, and we sending that to the discriminator will give us that, okay, I got real images, so this is one, right? And think about it, real images are 1 and fake images are 0. So what is the range in which this d of x can go to, Ritvik, if you can say that?
Sorry, can you come again?
Oh, so I said that the discriminator upon getting real images gets 1, upon getting
Mm-hmm.
fake images gets 0. What is the range in which the
0 to
discriminator is
1.
going? 0 to 1, right?
Absolutely.
And and now I'm going to my favorite graph calculator and just plotting out log of x. This is essentially what we do, right? This is essentially what we do, log of x, where x is just the the probability of the discriminator getting x. So we have something like this. And we say that we want to maximize this term. Why do we want to maximize this term, you might say? We want to maximize this term so that x moves from 0 to 1. When x moves from 0 to 1, we are saying that if we have real data, we want the discriminator to always say 1, which is real. So we are forcing the discriminator to always say that it is a real image only when we get a real image. So the condition being, give me 1 when you have real images. We are not talking about fake images at all. We just want to maximize this term. Does that make sense, Dev?
Absolutely.
Cool. Now the second part of the equation. Just as we did here, X was sampled from the real data distribution. What we do is we sample Z, that is the noise, from a noisy distribution. That is the distribution of Z. Yeah. And now we have this term of log 1 minus d of g of Z. So what does this mean? Let's peel the onion layers. The first part is g of Z. G of Z gives you, when you put in Z, that is the noise, the generator generates an image, right? And what is this image? The image is a fake image, as we might know. The generator cannot generate real images, it can generate real like images. That is what they already has, you know, told us lot of times. So now when you have these fake images generated by the generator, the discriminator should tell you fake images. But what happens is, let's go to Desmos again. So here what I have plotted is log of 1 minus x. Now we want to minimize this term. Upon minimizing, what we can see is x goes from 0 to 1 again. Now when x goes from 0 to 1, this means that we want this term, that is d of g of z, to be 1. What does 1 signify? 1 signify real. So what we mean to do is we want to create such good quality images which are very close to real images that the discriminator is fooled enough to say that these are real. So does that uh, how does that make sense, you might say? It makes perfect sense. The discriminator, upon getting real images, needs to say that it's real, 1. The discriminator, upon getting fake images, the generator should be so good that the discriminator tells 1 again and it fools off. It fools and it says 1. Yeah, Dev, do you have anything in mind?
Just a disclaimer to the viewers: if you are anti-math gang, don't worry, because this part is we'll explain how you can code this part, and that is
Right.
one of my favorite things to do about GANs, like that, the part where we essentially recreate this equation. So hold on tight.
Right. So that 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 is in fact a good thing to say. Like we often get overwhelmed with the mathematical equations, as far as I understand it. But reading papers, I think my colleagues will also concur that reading papers, we have always understood that um, how to break down a mathematical equation into code so that it's easier for us to process. Even with little to no prior knowledge about, say, mathematical symbols or something which kind of overwhelms you by just looking at it, don't just leave hope. Go to a PyImageSearch tutorial. You will find something or the other on the internet where we cover that paper. Or if we have not, please reach out to us in Twitter and we will. Uh, So having said that, we always go for a code first approach. We do make sense of the math as we are doing right now, but a code first approach kind of tells you how a paper or a symbol or a mathematical equation can be deciphered as code and you can run it. So that being said, this is the min-max game. This part, I'm just going to repeat again. This part is going to be maximized. So the discriminator, upon giving real images, gives me 1 and says, right, yeah, this is a real image. And this part is going to be minimized, wherein the generator is so good that the discriminator is fooled to give it a real image. Like it says that it's a real image, right? So this was the Desmos demo that I had created.
Can
Yeah.
you go back to the slide and just
Right. Yeah. Sure.
talk about what is V of D comma G, because that is a
Mhm.
question that we see popping up, and
Right.
there is also questions about like whether the discriminator is used to train the generator from the very beginning or whether it comes in later on.
Right.
But we'll get to that later. But we, just because we are on the equation right here, maybe you can elaborate on V of D of G. D
I
comma
mean,
G.
Right.
just
So
before
that was a
Auditra
good
takes over,
question.
I will just say that, like, whoever asked the question about the discriminator training the generator, hold on, because it's going to get much very fun. But yeah, you're correct actually. But yeah, hold on till we show you the code. Don't worry about that. It's very fun and intuitive as to how it happens. So we'll get to that.
Dave proceeds to just answer the answer the whole thing, spoils the entire thing, and says to hold on. I'm just kidding. Going back to what V of D of G is, this is the loss equation. That is a cost function, as we most probably know what a cost function is. So the cost function is the signal that the discriminator and the generator get, and they backpropagate the gradients with respect to this cost function and tune the neural network. So that is how a neural network works. A neural network, upon getting some inputs, and this is strictly on a supervised regime, upon getting some inputs, it predicts some output, and the real output and the predicted output they have a loss, and the loss is calculated, and the loss and the gradients with respect to the loss are backpropagated, and we tune the networks. This is the V of D of G is the loss or the cost function that we are going to get. And there is these two terms, that is min of G and max of D. That means in this part, as I have already told you, this part is maximizing D. That means that the discriminator gets to maximize this term, while on this part the discriminator is not learned at all. The generator kind of minimizes this entire term, hence the min max game. Does that make sense? And about that question, where when do we train the discriminator and when do we train the generator? So what happens in a GAN is that the first part of the training, we train like we send the data, real data, to our discriminator, and we do a basic image classification and we train the discriminator. And on the same epoch, just right after that, we create the fake images, we discriminate it, and just train the generator and keep the discriminator away, right? This entire training regime is covered very well in our Introduction to Generative Adversarial Networks by Margaret, and she's also the one who created one of our sketches, like the first sketch that you saw about the generator and the discriminator. So those were like nice illustrations, and I had to use them. And please go to Introduction to Generative Adversarial Neural Networks. We have like properly covered everything that there is to GANs, and also how to train them, right? Does that answer, Ritvik, the questions?
Yes, I think so.
Cool.
And we can move on.
Cool. That was something. And from there on, now I would like to take some time before we start off with SRGANs. I'm just teasing our audience, like, give me super resolution, give me super resolution. So what happened is, we at PyImageSearch have always looked at super resolution as a brilliant application to work on. So what is super resolution? If you ask, I'll defer that to Ritvik, who is a photographer friend of mine, who is also a deep learning expert. But hold on to that thought. Before going to super resolution, I just want to introduce Devjyoti, who is going to lead our session from here on. He's a prolific writer here at PyImageSearch, also a deep learning associate. And what he did before ESR and SRGANs is uh, pixel shuffle, which is also a good architecture and a very simple one, to be precise, which gives you like great results. And we have this blog post written out by him, and I am very honored to say this, that this blog post got like mentioned and tweeted out by the none other than François Chollet, the creator of Keras, stating that this is one of the good blog posts written in TensorFlow and Keras. And I would really want you all to go through this, wherein we don't cover GANs, but we cover super resolution and an architecture which is very simple but gives you good enough results. So no delay here. Ritvik, go ahead with your description about super resolution.
Before I go,
Mhm.
I just wanted to mention that some people asked about real life applications of super resolution, and whether super
Right.
resolution is actually applicable in the real world. And so what is super resolution? And before that, to the very beginners of computer vision, we have got you. What is resolution? So imagine that you have a picture, and you need to take that picture and push it to a screen where the screen is larger than the picture itself. So what you will essentially need to do is scale it, and by scaling it, you will take the corners and the edges of the picture and push it to the far corners of the screen. Now, what that is going to do, if the picture does not have enough resolution, is it is going to put information in places that it does not have information about, right? So if it has a lower resolution, which means it has lower number of pixels or lower number of information per pixels, it is going to try and create those information once we are stretching it. And what that will do is it will create artifacts. It will create noises. So artifact means the bad patches that you see on blurred or really bad images that you sometimes download from the internet. And that is all an effect of not having the right resolution. So now you get a sense of what super resolution means. It means that you take a smaller image, you take an image probably which is pixelated, and then you put it in a black box, you put it in a box which is your deep learning model, and the deep learning model gives you an image of a higher resolution. So the part where I said about magically putting information in places where it does not exist, that's what the deep learning model is doing, right? And now you might again be thinking, what is a real life application of this? Where am I ever going to use this? Dave, you want to say something?
I mean, yeah, this is just a part which I like a lot, because people, it's all around us in our daily lives, and we kind of fail to notice it. So I mean, just look around you. You have a film from 1950s, like the film which had the record for Oscars before Titanic was, I think, Ben-Hur. It was 1959.
Right.
At that moment, at that period in time, we didn't have technology like 4K, 8K, or whatnot. We didn't have that, right? Did we? Or I'm not sure. No, I'm just kidding. We did not. So how can we expect to preserve those films from that era and to, like, keep them alive in 2022, where we can actually see them in some 2K or 4K resolution?
Exactly.
Answers? Ritvik?
Super
resolution.
Exactly.
and yes, so there are ways that you could, like, computer vision is not a new topic. It has been around since like the last 40, 50, 60 years maybe. And there are ways where you can create simple, interpolation filters that give you higher resolution, but they also have upper limits. They can only give you a resolution till a certain point. After that certain point, if you need to blow it up till 8K, if you need to create super resolution on images that are not technical images that you see every day, you will eventually need deep learning. So
before
yeah,
let's
sure.
just address the questions, I guess. We have some questions.
Yeah. That's a good pointer to just take a breather as well, Ritvik and Dev. I'm just going to take a few of the questions. Maybe we could discuss as we go along.
Sure.
So Andrew asks, can we improve resolution of satellite images? You surely can, but satellite images are drastically a very specific zone of images that we are talking about. So it does not really have to, you have to be you have to be with an expert to understand which features of the satellite images need enhancing, which does not, so you get a scaled up image or a highly super resolved image without getting artifacts. Because as far as I understand it, satellite images have like small dots which can mean houses, which it can also have a stream, it can also
Or
have
it can
roads.
also be noise.
Exactly, that is what I was coming to. So GANs, the generator, kind of gives you real like data, right? So it can also have artifacts which are very bad for satellite images because they are very specific. So I'm not taking away all the limelight from GANs because they are good at what they do, but with some specific loss or some specific tasks at hand, they might be able to do satellite imagery super resolution as well. So having said that, let's do, can SRGAN be used to improve the quality of an image? If I do not want to increase the resolution, but just want to deblur or sharpen and create a crisp image and then resize back to original dimensions. That's a good one. Dev, Ritvik?
It doesn't have to be called SRGAN for that. If you have a data set specific for that, you can actually achieve it. Probably that probably can be your own architecture. But it doesn't have to be SRGAN. You can use SRGAN's like model details, but I don't think the task itself falls under super resolution, right?
Right. Not only super resolution, the task also does not fall under generative adversarial networks.
However, just a thought. The whoever asked this question is a smart guy, because if we do like, suppose we have an image with resolution 800 cross 600, and we want the resolution to be intact, but we want the image to be more sharper. So we can actually scale them down, apply super resolution, add crispness, blur, anti-blur and whatnot, and then we can apply super resolution and scale it back up. So that means all the complex computations will happen when it's in a lower resolution state. That means your training will happen faster. So that was a good question, I think. Yeah.
Right.
Like,
so
token of my appreciation for whoever asked the question.
So that is Nikunj. Token of appreciation from Devjyoti means nothing, but anyway, I also want to keep the session moving. So if I have missed out on your questions, that is my bad. I take full responsibility, but please don't send me letters. And Ritvik, we can move ahead.
Sure. So I think Dev would like to explain SRGAN and ESRGAN over here.
Yeah. So can I get the slides up if it's okay?
Sure.
So just another thing, if you're not yet sold on SRGAN or SR super resolution, for the gamers out there, DLSS, what NVIDIA uses, deep learning super sampling, it's actually kind of super resolution. So it's all around you. You just need to look at the right places.
And I'm getting that printed on a t-shirt.
Everything I say should be printed on a t-shirt.
Cool. Is this up?
Yep.
Yeah.
It is.
Absolutely. Thank you. So it was like super resolution existed much before GANs came into existence. Obviously, like we had it before deep learning became a big thing, right? We have naive bicubing, resizing, and techniques like that. But like those are like hard coded stuff. They're not learning anything, right? So when deep learning came in, it's like you're learning which features to be enhanced, which features you need to preserve, and like once it learns which features it need to preserve in a lower resolution, and then it upscales it, everything is intact, and you have an image which is essentially a pitch perfect copy of the low resolution one, except it's in a higher resolution, so obviously the quality is better. So it wasn't long before GANs would attack this domain and take over. GANs are like very mean. They always come into a domain and just top it because they're just too good. So then that's the moment where we had super resolution generative adversarial networks. So uh, uh, to my fellow authors, would you like if we kind of spoke about the paper a bit before we moved on?
Sure. Absolutely.
Yeah, absolutely.
Yeah.
Let's do that.
So, or you are our resident. You have like I think this was coded by you. So you tell us any insight that you would want from this.
Insights, many. I would really want to talk about the data processing pipeline when we go to the code. So before that, there is this only one thing that I want to share out, maybe because we are talking about the paper as well as how to read a paper is something which I would always want to let people know, because I read a lot of bunch of papers, and there is something called as research debt and all that stuff. So what I want everybody right now in this live event to take away from whatever I did is that don't shy away from reading papers. Take a paper, read it. Even if you don't understand it, that's perfectly fine. I don't understand a lot of paper. So I'm sure that Ritvik and Devjyoti does not too. And one thing that I would always like to say, and I support this to a very intense, I support this intensely, is that get peers inside your research work. I know that I have Ritvik, I know that I have Dev to talk about a new paper that has been released in, say, CVPR or any tier 1 conference. And what it tells me to do is that, Ritvik, I read this paper. Have you read this? He says, yeah, I did. And I didn't understand this part. And we now are in a sort of discussion. So what I want you all to do is go into PyImageSearch University, because we have a lot of fellows. We have a lot of peers just waiting for that one person to start a conversation, spark a conversation, read papers. And if you find that we have already covered the paper thoroughly inside our blog posts, videos, collab notebooks, or code zips, you're good to go. But if you think we did not, reach out to us. We will get it sorted out if we think that it has an impact. Yeah, that was about it. So don't shy away from papers, build peers, build networks, and you'll do good.
That was actually very insightful, if you ask me. So anyway, let's move back to SRGANs. So on the screen, if the screen is visible for you guys, you can see a picture of a tiger getting enhanced, but that is not what we are looking at. We will look at right now. Let's look at what's on top of that. We have an equation that is LSR equal to LSR x plus 10 to the power minus 3 LSR gen. So that might sound a bit gibberish to you, but let me give you a spoiler alert. Essentially, that is what SRGANs are. So because that's where the secret lies. The authors of GAN, they were pretty smart. They were pretty smart for grasping the thing that, like, the fact that they can be the first people to capitalize on this domain, and they did it pretty well, because like let's take a bit of a recap to what GANs are, as Orithro had already said. GANs are what is, we have a discriminator, we have a generator. The generator is trying to create data which is which has to fool the discriminator, while the discriminator is also learning how to better judge data. So in SRGANs, the core idea is kept intact. but we are doing it for a very specific task, that super resolution. So some things are changing. So let's go over those. First things, in a normal generator, we are sending in random noise as input, which is getting modeled into some image. But in super resolution, we are essentially sending in a low resolution image, which is getting scaled up into high resolution. That's the first change that happens. We are not sending in random noise, we are sending in a low resolution image through the generator. You guys agree, right?
I do.
I do.
Okay.
Yes.
Okay. And the second thing, you people might think, so the laws that we can see here, this kind of seems a bit complicated. Like super resolution could have been achieved simply by the way the Minimax game, that the generators like the GANs train with it, like, right? Or you had actually
Right, right.
asked me the question a few days ago, right? Yeah,
Right.
you could have achieved super resolution just with the adversarial loss itself. That is the loss that Orithro had explained, the big equation, which might have been a bit scary for anti-math people. But so that's where the SRGAN authors added their magic. They essentially developed something called the content loss. We have the normal generator, normal adversarial laws, that is the discriminator and the generator training. But they asked a very good question. We can recreate data, but what about the finer details when we are actually doing the super resolution task? The finer details, like inside an image, there might be a little some little artifact which is important. Sorry, artifact is not there. Some little feature which is important.
Mm-hmm.
Now, when we are just adding adversarial loss and recreating the image, that those artifacts might get lost. So we have to reinforce the loss somehow, and
Right.
that reinforcement is done by the content loss. And what the content loss is something that I will go like obviously explain while we are going through code. But essentially what it does is it makes sure that our predicted, the fake image, is is grows more and more closer to the real super resolution image,
Right.
right? So do you guys have anything to say about this idea, like this is reinforcing the loss?
That's like pretty ingenious and pretty simple, to be honest. uh, I wonder how they came up with that, but like there are a few questions. Can we pause to take them now, or like should we take them later on?
So we can take them. Let's go on.
So there's a question from Sonarianable. I do not know if I'm pronouncing this right, but now the question is, if they have a slightly shaking camera, can they enhance SRGAN by putting the input to a bunch of similar images, thus providing more info to the network? I think this will be covered in the code where we do augmentation, and we do not do shaking camera augmentation, but we do something similar.
That
But
becomes a bit of a different task, but I guess augmentations are a good way of looking at it. That was a good one, Ritik. Thank you.
cool. And there's also some questions about whether generated images will be recognized in a court as evidence. I don't know. We are all deep learning
Oh, that
engineers
is
here.
actually a pretty like pretty nice question. Now, so this is something that I read a few days ago, not few days, a few months. Let's be honest. In some places, you might have traffic cameras, like traffic cameras which are like pretty bad quality. So the pictures that they will take are low resolution, so you can actually enhance them. That is actually used. Anyway, let's move on.
Yes. And so there's also another question about how the random noise is different from recent diffusion being used in DALI 2.
I
Or
love
sure.
this question now. This is a good question.
We have a resident DALI expert, so please take this.
No, no, I'm not. I'm not a DALI expert, but what I can say is just a sneak peek to what PyImageSearch is cooking. We have a really big series on transformers that is going to come anytime
Yes.
soon now. So I'll skip this question as if I did not see. So, so just hold on, and we might come up with a live session about transformers too. Who knows?
Yes.
Spoiler alert, we will. Okay.
And there's a few questions about the original size of the high resolution and super resolution image. So like all of
I
that,
mean,
how
that
many
is
patches, all of that will be covered in the code. So I'll leave it to Dave to
patches,
go ahead.
patch can. Okay, yeah. So I will be moving on, and the size questions and those are specific ones, and those will be answered in the code itself. So please hold on a teeny bit more time because I still have to go over the architectures. So what are these, like the first key factors are gone, like we are feeding instead of random noise, we are feeding in images as input to the generator. The second one being that of the content loss, which we will be explaining in detail later on. So what are the kind of secondary points to note? So now we come to the architecture. The generator uses residual blocks, and the idea behind residual block is to keep information from previous layers alive by making skip connections. And you're essentially also giving your model to an array of features to choose from. So Ritik had made a very good analogy a few days back. It was about this being like a flashback. So you want to talk about that, or should I just move on?
Yeah, I mean, it would be helpful if you have the architecture up, I guess.
Okay, then let's talk about it when we are going through the code,
Yes.
I guess. Yeah.
Yep.
So yeah, remember residual blocks. So the discriminator network is pretty standard. It kind of works like a normal discriminator would work inside a normal GAN. So again, the key factors: content loss, image getting fed. Then the secondary ones, the generator uses some residual blocks. So keep these things in mind, because enough talk. We are moving on to the code. Is my screen visible?
It will be in 1 or 2 seconds, I guess. There you go.
It's visible, right? Everything?
Yep.
Yes.
It is.
Okay. So if you actually are part of university, I think you already have the codes and stuff. So but I'll still go over the directory once. So in the SRGAN directory, we have the outputs folder where we are essentially going to store our outputs, model rates, etc. And the PyImageSearch directory. So we at PyImageSearch, if you are familiar with our way of code, we kind of like believe in extreme modularity, and that that caught me off guard when I started here. But moving on. So inside the PyImageSearch directory, we have an init.py. If you are not familiar with it, just think of it as a script which turns this entire PyImageSearch folder and makes it work as a Python directory. Then we have the config.py. So we always create a separate config.py where we store the entire configuration pipeline for our project, which we use. So this is essentially contains variables. So we'll go over them. We are importing. We are going to import OS because we have some paths to join. And for people who are not familiar with this lingo, just think of whatever we are going to import. Think of it as your allies who are going to help you code, because that's what I always tell newcomers. They are basically going to provide you with help, which are basically functions, which will help you reach your end goal of the code. The data set is div2k. Now, Orithro or Ritik, do you want to talk about div2k? Because I mean, you know me, like whenever we do some super resolution task, we always go to the div2k data set, because if you go to the div2k site itself, they say it themselves that they are like, the whole point of this data set is to like work on super resolution tasks. So that is what we have used for our project here. Then we have something called the shard size. We have shard size is something that is going to get used in the TF records, and we have a resident TF records expert here. Orithro, would you take this?
Yeah, so just going due to the fact that we are already on the configuration stage, and we also have a question about the architecture of the model. So what I would want our audience to hold on to is that when Dev goes into the code, he will not only describe how the architecture looks like, he will also bring up images so that we can, have a comparable, we have a comparison in hand about the code and the architecture, how it looks and how it looks on code. So maybe we could hold on to that thought. And while we are at configurations and datasets, I'll just quickly go about how what was the thought about creating TF records and not using like TF data as it is. So as I said, GANs are terrible to train, not stable at all. You have to babysit and all that stuff. And on top of that, if you have diff2k, which is like a really big data set, what happens is it's going to take a lot of time for you to babysit. And I am not the one who with a lot of patience. So what I did is I quickly took a cluster of GPUs and also TPUs, by the way, because this one project about ESRGAN and SRGAN does not only let you know what GANs are or how to apply them on super resolution. We also take like good care about our readers and also let them know how to train it on TPUs and GPUs. So that is a good thing. Now, due to the fact that I wanted to train it on distributed setup, I quickly took all the data like the diff2k and built TF records out of it. Why do we need TF records? We need TF records because it's a file of storing binary data and it's very efficient that way. It reduces the size of the data firstly because it compresses to binary byte strings, and also due to the fact that it is based on Google's protobuf, which is a communication scheme and also a way of storing data. It is also very efficient to be sent out over the internet. Now what happens with a TPU is that TPU is somewhere off on cloud, and you can have your TF records somewhere in your GCS bucket, that is Google Cloud Storage. So it's kind of a server. So both are living at different places, different servers. Now if you have a text file or something like that which takes a lot of time for that going from the bucket to the server or bucket to the TPU, it's going to take a lot of time for the TPU to ingest the data. Now what TF records does is it creates so seamless, efficient communication that the TPUs can ingest the data within seconds. Now, what happens with TPUs is that the more throughput of data, that is, the more it can consume the data, the better it learns, or not better. Let's not term better. The faster it learns. So it gets a lot of data, it trains, and it spits out a lot of data. So that is why we took TF records. And now about shard size. So this is like coming to us full circle. We started from shard size, we went to TF records, we went to TPUs, we went to GPUs. Now coming to shard size, what is a shard? A shard is broken pieces. Now if you have diff2k and if you know about clusters of GPUs and TPUs, they always come in a form of like more than one. So cluster of GPU is a GPU which is more than one. A TPU consists of 8 TPU pods or 4 TPU pods, however you want it. So when you break the data and asynchronously put it in all of the hardware all at once, so think about it. If you have one image and it takes 60 seconds for one GPU to do, now what happens when you have 6 GPUs? It's going to take 10 seconds each, and due to the parallelization you just need 10 seconds, right? So from 60 seconds comes down to 10 seconds. So this is the power of TF records and sharding and batching, which we cover in depth inside of our tutorial, and we'll also have a following tutorial about TF records and TF records only. So hold on to your TPUs and GPUs right before we dive into more of the questions. So yeah, that's about it from my end about the
Uh,
data pipeline.
to our audience, if I want to, if you want me to dumb that down, it'll make your work faster.
Yeah,
Sorry, Arithur. Really
absolutely,
sorry.
absolutely. No,
Yeah.
don't be.
So
Uh, so
moving
yeah,
on.
it's going to make your life easier. You have to babysit a model which
And
you had to for 8 hours. Now you have to
and
do
we
it for
also
about 1 hour.
saw some comments about how
Mhm.
we can be efficient with our computation. So here's the answer.
Yeah,
Voila.
use TPUs.
Okay, so moving on. The next variables we have is the train batch size, infer batch size. These are obviously pretty standard run of the mill work. So the question, I have seen this question appear a lot. That is the high resolution, the low resolution shape. And now please do not come with us with pitchforks. So a low resolution shape is 24 cross 24 cross 3, and the high resolution is 96 cross 96 cross 3. You might ask why the small sizes, and to that answer I would say because GANs. We don't have that much, like we can't just give 1 or 2 days to train something like this. And so we had decided to, for sake of simplicity and for easier computations while training, we'll make the sizes a bit small, but it's still going to eventually achieve what our target is. So yeah, since it's 96 and 24, 96 divided by 24, quick maths, scaling factor will be then 4. So we have 4. So the GAN model specs, moving on. Number of filters is set to 64. Our residual block is set to 16. The residual block, do not get worried with the naming convention. Don't. It's just a combination of layers which we will come across when I will be going through the architecture. Leaky alpha is the leaky ReLU parameter, that's 0.2, and the discriminator blocks is also is 4. Again, discriminator blocks is a combination of layers which again we'll come across when we'll go through the discriminator. Now, so Orithro, why have we a pre-train LR as well as a fine-tune LR? Please, can you tell us?
Right. So, right at the beginning of our live session, when I was kind of explaining about the GANs, we knew that generators have a very big task at hand, while a discriminator, not that much. Why do I say that? Because generators need to take in random noise, but not here. We take in lower resolution images. We provide higher resolution images, but the discriminator has only one thing to do. It just says whether it's real or fake. So it's basic image classification, which we can do in what, like 15 minutes with TensorFlow or PyTorch or whatever. Now the generator being on due to the fact that a generator has to prove its point, it has to train for a longer period of time, and it also has to compete against a discriminator which is already at a greater stage. So if you want to talk about an analogy where we are talking about athletes, so a generator needs some warm up before running that sprint, but a discriminator does not. And maybe the discriminator is starting off from the 50 meter mark in a 100-meter dash. So what we need to do is we need to pre-train our generator, just the generator, with some kind of loss, which Dave is going to obviously cover in his code walkthrough, with some kind of loss which makes the generator warmed up for our 100-meter dash. And while that warm up, the discriminator is not getting trained. Hence, even if it starts at 50-meter mark, the generator is confident enough. Now that is how I can beat you, discriminator, right? So this is what basically is. We pre-train the generator, as in we warm it up, and we don't warm up the discriminator because it's already going to, have a very easy task at hand, and hence the pre-train and fine-tune.
Yeah, so again, just to reiterate what Oitro said, the pre-train LR and the pre-train epochs, these are only for the generator and not for the discriminator. But the fine-tune LR and the fine-tune epochs, these are when we are considering the GAN as a whole and not just the generator. So keep that in mind. So these is where our config pipeline essentially ends, because these are, the rest of it is just paths. And since Oritsu is going to run inference for us, we don't really need to go through these paths again, obviously. But if you want the code, you can obviously sign up for university anytime. So we'll move on to the next most important thing about our project. And I'm going to ask this question to the chat as well as to my colleagues. What's the most important part of training a GAN?
Data.
The data.
Absolutely. If you don't have enough data, you don't have good data, then I don't really see any point in training the GAN at all. So that is for that reason our data process.py script, the next script, it contains tons of augmentation functions, because we apply data augmentation, we get the same data, but we are essentially augmenting it. So that's going to appear as some different data to our model, because obviously a model does not work as our brains do. We can understand if an image is flipped, but for a computer that would be something totally new. and that's spatial invariance, and that's something we also have worked on. I don't want to be like go on another parallel, so we'll just go through the first function. We have random crop, which takes in the low resolution image, high resolution image, the HR crop size, and the scale. So the thing is, when we are grabbing data from the diff2k data set, we can it can be of any size, but at the end of it, we want our low resolution image to be 24:3, and high resolution image to be 96:3. So what this function does essentially is just randomly chooses a patch to be just cropped out in the shape of 96:3. Am I right, Orithro?
Absolutely.
Yeah. So that is the job of random crop. In the end, we want our low resolution image and high resolution image returned as a set, so that those are still the relationship between them is still alive. So we'll also have to make sure that the same the corresponding regions of the two images are cropped. This is actually something that Orithro faced, but I will talk about that a bit later. The next function we have is get center crop, which essentially takes the same arguments as the random crop, but as the name suggests, we are just grabbing one particular center crop. No random crop. So we are telling it from before, and okay, zero out on this particular area. Get the size to 96:3, 24:3. Return the images. Job done. That is exactly what it's doing. Next, we have random flip. So based on a probability value, this is fun, because based on a probability value, the images can be flipped from left to right, or it can be kept as it's in its original state. So Orithro, you had a story about this, so I want you to share this with the general audience.
Right. So this is a very embarrassing story. I don't know why I am always made to say out my embarrassing stories in front of the whole wide world. But in random flip, this is an augmentation that Dev has quite correctly said, that depends on a flip probability that the images are going to get flipped. Now, what I did while I was coding this project is that I use two flip probabilities for each and every individual image. That is, the lower resolution image gets a flip probability in its own, and the high resolution image gets a flip probability on its own. Now, what this did, this silently broke the entire GAN architecture, because the real image with which the loss is going to get calculated could have been flipped, while the resolved image or the data augmented image was not. And that created a problem, because that is not deterministic. I need a deterministic way of knowing that the low resolution image and the high resolution image both get flipped or not flipped. So that was one thing that I did and broke the GAN, and I'm sorry about that for taking 1 day or 2 days to debug it.
Yeah, so remember, when you are applying augmentation, make sure to keep the relation, like correspondence between the low resolution and its corresponding high resolution image, that relation alive, because you don't want one image to be flipped and the other to be stayed at the same, because that's going to create lots of problems, trust me. So yeah, moving on. Or Ritik, do you want to address a few of the questions, if there are any?
Not really, but there is a question about whether augmentation can be applied when dataset is small and not enough, and whether it is used for active learning. So, and there's a question by Gaurav whether deep learning is used. Yes, the cream of deep learning is used here, GANs. And so, yeah, there's a question from Iman about whether this is used when dataset is not enough.
Yeah,
and
well,
that is true.
the answer is you have to. You have no other option to not use it. The only way you
Yes,
can
GANs are
keep
infamously
stretching out-
data handling.
No, it does not only apply on GANs. Even if you have less data, you just have to try and like milk out as much as you can from the particular data. So apply
Right.
as much augmentation as you can. So okay, yeah. Moving on. The next function is random rotate. We have it takes in the LR image and the HR image as its arguments. So based on a number, here we are using tf.random.uniform with the max value 4. So the numbers can be 0, 2, 3. Based on that, we are rotating the images certain degrees. So the 0 means there is no rotation, 1 means 90, 2 means 180, 3 means 270. So based on n, it's going to get rotated. So it might be so that the n is 0, so you don't have any rotation, but or it could be that it's totally rotated. So it's fun either way because your model is still learning.
Right.
So next we have read train example. So this is essentially another part of TF records. There's nothing much to discuss here. It's essentially that we are creating a feature template here. It's a dictionary where the keys are LR and HR, and it's a fixed length TF string because, as Orithra had said, when it's TF records, the images are converted into byte strings. So that's what we are referring to here. So we are essentially parsing the low resolution image and the high resolution image from our example argument here, and grabbing those images, we are just applying all possible augmentation possible, except for the center crop, which we are not using when we are in the retrain example function. Remember that here we are only using random crop, random flip, and random rotate. So once we have applied all the augmentations, we can move on, reshape the images just in case to 24, 24, 3, 96, 96, 3, and then return them. And that's our retraining example done. Now we have retest example. We are starting with the same thing. We are parsing the low resolution image from the example, high resolution image. And here we are not applying any augmentation apart from the get center crop. Now this is very interesting because you really don't have any leverage or any basis on applying augmentation to your test dataset, because that's not on which your model is going to learn.
Exactly.
You need to have your test dataset in such a manner that the outputs are discernible by you yourself. So that's why we are only applying the get center crop here, so that no kind of rotation or any kind of hooper do is applied here. Again, reshape the images just in case 24, 24, 3, 96, 96, 3, return them. Then we move on to the load data set, which takes in the file names, batch size, and a bool variable called train, which if true, that means that the load data set is loading the training data set, which when false, the load data set is loading the testing data set.
Or the validation data set.
Yeah, validation data set too. So we are going to get the TF records from the file names right here. And if it's train, if this is true, then we will map the read train example function, which I had just explained. This one where we are applying augmentation. If we will just map the read train example function to all the elements inside the data set. So that makes our lives so easier. We don't have to just loop over all the elements. We can just directly map the function to all the elements, and all the augmentation is going to get applied by itself. That's quite fun, isn't it?
Absolutely.
Yeah. So else, if the train is set to false, of course, then it's a testing or validation data set. So we will be mapping the read test example to all the elements inside the data set. So that done, we will just batch, prefetch, and repeat the data. Our data set is ready, so we'll just return it. So cool. Every prerequisite is done. We can finally move on to the GAN architecture. I know you guys have been waiting for it for a long time. Really sorry. So let's move there. Again, as I had said, in PyImageSearch, we believe in modularity. So inside the SRGAN.py script, you will find that the complete SRGAN has been packaged into a class. And actually, that's a pretty good practice. So please, if you do code it, try as much as you can to code in classes. So the first function is the generator, of course, takes in the scaling function, the number of feature maps or number of filters, and the number of residual blocks, which, if you remember, the configuration we had set to 16. We'll start off with initializing the input layer. Here we have a rescaling layer. What that is doing is our image pixels are 0 to 255. They're getting a map to 0 and 1. That is all it's doing. That's getting rescaled. Then the xn is passed through a conv2d layer. And the feature maps is the number of filters as in the arguments. That is getting passed through a parameterized ReLU function. Now we'll construct the residual block, basically. So we have the conv2d layer.
The flashback.
Yeah.
Yes, that is a flashback.
The batch normalization layer, the parameterized ReLU, another conv, another batch normalization, and here we are doing the skip connection. So here you can see that this here x, the last here, the line number 30, x equal to, I'm just going to zoom in a bit more for our viewers. So line number 30, we have batch x equal to batch normalization of the previous layer. So x skip adds this and this all the way it's going back to the xin, which was where we had applied the parameter as rel. So it's just add the key, like making a skip connection, keeping the information from previous layers alive. And that's resnets, that's extremely popular and that's extremely ingenious. So this particular combination of layers is essentially going to be our residual block. So we will start a loop and keep adding this particular combination, where we will add the x skip at the end, which will just join the first and the last layer of the like the series of layers. So that's going to keep create the skip connection. So once we're out of the loop, we'll have a final conv2d, a batch normalization, and and final add layer, which is going to add this layer all the way till here. Talk about time traveling, if you ask me, all the way back till where we had created the parameters rel. So imagine if you have like 100 residual blocks, it's going to go back and back and back and back and back and finally connect that. So that's like a big thing, I would say. So here next we are going to have a conv2d layer, where we can see that the number of feature maps is a bit different, and why I will come to that. And then we come to arguably my favorite part of pixel shuffle super resolution, the block that we had mentioned earlier. That's that TensorFlow function called depth to space. Believe me, it's not a learnable function. It's a hard-coded function, but it's beautiful. And I'll be using a picture here just so that I can explain better. It's visible, right?
It is.
It is.
Yes.
Yeah. So what depth to space does is that it decreases your the channels of your feature map, but increases it height and width wise. Very complicated lingo. Let's just see an example. So here we have a feature map. It has 4 channels: blue channel, red channel, yellow channel, and green channel. So the blue channel is 3x3, red is 3x3, yellow is 3x3, green is again 3x3. So when we are applying depth to space, it is now a single channel. But you can see that if we see the shape of this, it's 9 cross 4, that's 36. And if we see the shape of this, 1 2 3 4 5 6, 1 2 3 4 5 6, that's 36. No information is lost, it's just reshaped. And it's a very brilliant idea, because if you think about it intuitively, your model has to bow down to the loss function. So if the loss function tells it to go this way, then right before this depth to space function, your feature map has to be in such a way that once the depth to space is applied, it goes to the right shape. So we are like, this is like, if you ask me, it's pretty fun. Coming back to the architecture, I will just zoom out a bit. Yeah. So this is repeated again here. Then we have a final conv2d layer, but notice here that the activation is tan edge, so the range of the pixels here will be -1 to 1. So we have to, when we are applying rescaling, that means when we are rescaling it back to 0 and 255, we'll have to make sure that the offset is correct. So we have a rescaling here. This concludes the generator. We will initialize a generator object and simply return it. That's the generator architecture done. Do you guys have any thing to add here, my fellow colleagues?
Not really. I'm interested to see how the results come out to be.
Same.
I'm interested to see how the training happens, because that is the most favorite part. So, moving on, discriminator. It takes in the number of feature maps. That's the number of filters in the conv2d layer. The leaky alpha, the discriminator blocks, which was set to 4 inside the configuration pipeline. You might obviously you can change it to anything you want according to your needs. First things first, we initialize an input layer. We apply rescaling here, and we rescale it to -1 and 1. Then we have a conv2d function here, a leaky relu function here. We have a conv2d function again, a batch normalization, another leaky relu. Now we will start looping over the discriminator blocks. So inside the discriminator blocks, we have a conv2d function, a batch normalization, and a leaky relu, and this is repeated. So we have three layers here, and this combination is repeated twice. That becomes our discriminator block. So we have 6 layers which are repeated 4 times. So we have 24 layers one by one, which is getting automated due to this hold. Once this loop is done, we'll apply a global average pooling, a leaky relu, And our final head, a dense function, which will essentially tell us if the image is fake or real. This concludes the discriminator architecture. We'll just initialize an object and return it. So, do we have any questions on the architecture, if any? I hope not.
Not a question, but an observation that a discriminator is fairly lightweight than a generator.
Absolutely,
So,
yeah.
so that
So you can actually intuitively think about this in the sense key discriminator is reading an image, it's telling it's real or fake. But generator, it has to recreate an image. So you might
The artist has to
be
work harder than the
harder.
art
Yeah.
critic.
Okay, so this is the next part is the SRGAN training.py script, and this is my favorite part. Please hold on. If you are made it till now, please hold on. This is my favorite part of explaining how a GAN is trained. So again, you are turning it into a class as the class SRGAN training. So the init function, pretty standard. We are just grabbing the arguments here and just assigning them to class variables, like using the self dot functionality, self dot generator equal to generator. That's pretty simple. That's fine. Moving on. We have the compile function, which has the generator optimizer, discriminator optimizer, BC loss, MSE loss, BC binary cross entropy. Aurithra, would you enlighten our viewers?
about the losses.
Yeah.
Okay. So MSE loss is mean square error loss, which means that you have two images or whatever for that matter, and you take pixel loss and square them and average them out. And binary cross entropy loss is where you have softmax or a sigmoid for that matter at a probability distribution in which you want to assess which category gets the most amount of weightage. So that is the kind of loss that we are talking about. So BCE loss is more or less used for the discriminator. MSE loss is for the generator.
Yeah, thank you, Aurithra. So we are just again assigning class variables using the self dot functionality. Now, my most important part of this whole thing, the train step. It takes in the images as its arguments. First things first, we will unpack the images. So images has the low resolution, high resolution corresponding side by side. We will unpack them into the LR images and the HR images. LR low resolution, HR high resolution. So now then we will be casting them to TF float 32 for computations. Obviously, this is just TensorFlow being TensorFlow. Next, we'll pass the low resolution images through the generator, and now we have a fake set of high resolution images, which is called SR images. Remember, you don't get confused with SR images and HR images. HR are the labels, that means the real images. SR are the fake images. Now we will combine the fake images and the real label images here. We'll combine them using the concat function. So essentially, just think of it as a sandwich with no meat inside it. So the lower half of the sandwich is the labels, and the top of it is the fake images which have been produced by the generator. So according to this no meatless sandwich, we will be creating the labels also, which we have done here. So obviously, since the HR images are fake images, we will be the labels for those images will be 0. So we have done here exactly that, and the labels for the high resolution images that are the real one, which will be 1s. That's done. So we'll initialize a gradient tape. So this gradient tape, if you're not familiar with it, just for now, just know this, that this is going to help track the variables, which will help for gradient calculations. Go ahead with that explanation for now. So we will be passing this sandwiched images to through the discriminator. We will get the predictions, and we'll calculate the discriminator loss by comparing them with these labels. That's pretty simple. So that is all that is happening inside the discriminator loss. We'll just compute the gradients here and apply the gradients inside to the discriminator. Discriminator is done and dusted. So now is the interesting part. We will be creating a set of misleading labels. So that misleading labels, why? Because okay, let's just move on. You will understand soon enough. So the misleading labels is labels which says that all the images are 1. So we will again initialize a gradient tape. We will generate fake images again by passing the low resolution images through the generator. And for these fake images, listen closely, for this fake images, we will have these misleading labels. So instead of this fake images having the label 0, this fake images now have the label 1. That's fun. So let's move on. So we will be passing these fake images through the discriminator and getting the predictions. And here we are calculating the adversarial loss, which, if you remember in the slide, it was 10 to the power minus 3. So we are doing that 10 to the power minus 3 into BCE loss, where we are passing the misleading labels and the predictions. And now is the content loss. So I'm just going to pull out an image here. So think of this Tetris block in the middle. These two are the same models, by the way. These Tetris block, it's a VGG architecture, a split VGG architecture. We are not going till the end of the VGG classification. We are just cutting it in the middle and taking a random layer output. So on the top, we have a fake image. We are passing it through the VGG and we are getting a feature map. On the bottom, we have a real image. We are passing it through the VGG and we are getting a feature map. The authors of SRGAN, they're smart. They want these feature maps to be as similar as possible. For those to be similar, what can you do if the weights of these VGG are frozen? So these VGG cannot undergo any changes. So how can you get these feature maps close to each other? To my colleagues, this question to you.
By making the inputs as close, like the fake inputs as close as the real one.
Ding ding ding, you are the millionaire. We don't have money, but we'll provide you with appreciation. So exactly, if the inputs are as close to each other, the output from this particular split VGG, these feature maps, will also be close to each other. So that's how the SRGAN authors are reinforcing the loss by making this simple addition here. They're smart. So they have to make sure that the inputs are as close to each other so that this output is also as close to each other. So that's exactly what they are going to use. So here they are creating, they are just initializing the VGG network, and here they're normalizing the VGG. So it's mentioning the paper that you have to use 12.75. So don't get worried using due to that. So we are going to do the same for we are going to do the same for the fake VGG and for the real image VGG, and we're going to use MSE loss to calculate the difference between them. So that is going to be our content loss or perception loss. So the total loss becomes this 10 to the power minus 3 into the adversarial loss plus this VGG output MSE loss. And now we are going to compute the gradients for the generator and apply them inside the generator. Now this is actually a very important junction, so I have to explain this a bit. Why are we misleading, like we are mislabeling the fake images? Think about it. It's intuitive. Because if the labels are fake and the discriminator gets the fake images that the generator has generated and tells this discriminator is pretty nice here. He's going to take the fake images and say, wait, these are fake. But we have provided misleading labels. So that difference, the difference in the labels is going to tell the generator that you're so far off from producing a real image. So that difference is going to tell the generator that is the amount of distance you have to cover, so that the discriminator, who is the nice person, is going to label your data as a real one. So you're very far off, but you have to make a lot of progress. So that is how we are using the discriminator to train the generator. Was I clear on this, my colleagues?
Crystal clear, I would say.
Yeah, so there was a question in the beginning, so that I hope that answers your question. So we are calculating how far off from an actual real image the generator still is using the loss. So that is going to train our generator, and we will return the generator, and that actually concludes our training. So the next part is where we assess the results, and Oritra is going to take over from here.
What I would really want, Dev, is to also, kind of showcase how ESRGANs due to the fact that you are already in the code walkthrough, how
Yeah.
ESRGANs differ from SRGANs, and then maybe I could take the inference all at once, both of them side by side.
Okay. That actually works. So you want me to explain ESRGANs too,
Yeah, exactly.
right? Okay.
Just to compare where
So
we change in the code.
so you just bring up the slides if it's possible.
Yeah, I'm
Sure.
sharing the slides.
Let me know when I should pull it up.
Yep.
Yeah, pull it up, please, right now, if it's okay. So meanwhile, how as I've been saying this from the beginning, this particular training part where we are using the discriminator to train the generator, that is my favorite part of in while coding out a GAN. So I hope the viewers till now are actually following and enjoying what we are putting through. Though. So if you have any questions, again, please ask away. So yeah, the slides are ready. So next, obviously, SRGAN is done. We'll go through the inference. Don't worry. So the things that we had to take in consideration. Number one, we are not feeding noise to the generator. We are feeding low resolution images to the generator. The number two, the perception loss. So I would say that SRGAN kind of peaked, peaked the use of GANs inside super resolution. So what do you do when you have already kind of peaked inside a domain? Or it's Ritvik?
Sorry, can I get that again? The question?
I think the question was, what do we do if we have peaked inside a domain? And I think the correct answer is to look for ways to,
Exactly.
improve, even if
Exactly.
that's not something that comes right off. But we'll just look for ways to improve upon that.
Exactly. Thank you. I had some disconnection issue. No, I hope that wasn't a problem. Anyway, coming back. So SRGANs kind of already had peaked. So where do you attack? You attack in the roots. So ESRGAN actually brings about certain changes which do not kind of attack, like change the general essence of SRGANs, but changes it enough so that the results kind of become even better and the whole process is more efficient. So what does enhanced super resolution GANs do? The first thing that it does is removal of batch normalization layers inside the generator. So the authors kind of notice this, that like the generator itself was kind of would be more efficient and faster, less complex if we removed the batch normalization layers entirely, and that does make the process faster. But obviously we know that BN layers are a bit more complex. The second change that they introduce is the residual in residual dense blocks. Remember when we spoke about flashback? This is like flashback and flashback. It's like Inception, because what happens is that instead of creating a skip connection from some layer to another layer, we grab a particular set of layers and we connect the outputs to each of its subsequent outputs, so that all the layers inside this particular block of layers will have access to everything from that came before. That is like providing it with as much information as possible, that information overload, but it works pretty well. So I guess it works for us. So that's a very smart decision, I would say. The third thing is what you see on your screen right now. This is a standard GAN. What happens in a standard GAN? You're sending the D is your discriminator. You're sending XR, which is a real image, and the real image is going to be said, okay, it's real, 1. And the second is obviously XF, that's a fake. It's going to be said false. Can you go to the next page, please? ESR GANs use something else. They use relativistic discriminator. So Orithro, I'm going to give this over to you so that you give us a general idea of what this is.
Right. So what happens with relativistic loss or relativistic GAN is that upon being sent a fake and a real image, we try to figure out is it more realistic than the fake data? Like if we send in real images, and we condition it on fake images, we try to figure out how much more real is the real image than the fake data. In a standard GAN setup, we just said, okay, it's real. But here we are saying how much real it is compared to the fake data. So we kind of relate, or we
So
kind
it's a
of
measure of relativity of how much
exactly
fake
how
it
much.
is to the real data, or how much real it is to the fake data.
Right.
Exactly.
And vice versa. So if we send in fake images and we condition it on real images, we just want to see how much of the images are fake or less real than the real image. So
Thank you. Thank you.
that should be, yeah.
That's a great take on it. So yeah, that was the third addition. The fourth addition is now that the loss is changed. And how is it changed? Like, Ritik, can you go a few more slides ahead where the loss function
Sure.
is?
I guess.
Yeah. No, sorry, the next one.
So the ESRGAN loss.
Yeah, yes, again, yes, again. Yeah.
Good.
Exactly. Thank you. Also, the images are all created by this one is created by Ritik. It's great, and we all know it's great. So yeah. So the now the loss is not only the adversarial loss plus the content loss. ESRGAN has now brought in another addition of its own. That is, it's going to compare the ground truth and the predictions directly. Now there is no in addition to a VGG output comparison, we are also comparing directly the ground image, a ground truth high resolution image, and the predicted high resolution image. That's like pixel to pixel loss. And that is going to reinforce the loss even further when we are trying to keep in mind that we are trying to upscale all the features inside the low resolution image alive. We have to keep them alive. So keeping that in mind, now the improved loss function is now building, like, getting reinforced even more. So ESRGANs have brought in lots and lots of changes. So you have to give kudos to the authors, because I would have probably thought the ESRGAN have peaked, but ESRGANs brought in lots and lots of changes, and we'll be going through the code pretty soon right now. So I guess you'll get to see that. So I'm going to share my screen. So is it visible?
I'm just going to pull it up.
Oh, that's great.
Yeah, it's visible.
Yeah. So the main parts of ESRGAN, most parts will be probably same, because the config we have the same. We have shard size, train batch size, the same shapes.
What we
scaling
could do
factor.
is, Dev,
sorry?
not like it's going to be redundant because there are a lot of overlaps between ESR and SR. Just the parts, the architecture or the loss that we had covered. Yeah.
Okay, pretty cool. So we'll directly go inside the architecture. So here we have created a class ESRGAN. First function is the generator, as always, scaling factor, feature maps, residual blocks, leaky alpha, residual scaler. Initialize the input, scale the input again. It's all kind of just a node to SRGAN what we had done. The change here is the residual block itself, which I am going to explain right now. So we have tried to follow the paper as much as we can, but obviously we were also constrained by computations and time, and so we came up with a way of adapting the residual block, but in our own way. So how we did that is here. So we start off with a convolutional con2D layer, a leaky ReLU layer. Then we have an addition. We instantly just add these two. So we are keeping the tradition of the residual block alive. We're just adding the input to the output to the subsequent input.
Right.
So we are giving it a con2D layer, a leaky ReLU layer, and then
That's
again
right.
adding it. So I'm just gonna call it LR layer for now. So please bear with me. So we're just adding it. So instead of the inputs having all the outputs going to all the subsequent inputs, we are just sending it to the directly next one, because if you think about it, some information from all the previous layers is still alive in this one. It can probably not be as prevalent as it would have been if we'd have chosen to go all the way,
but it's still prevalent here. And if you really want to go through a residual and residual block, we have actually used that in our pixel shuffle super resolution blog post. That's where we had actually utilized it, because that's not a GAN, so it's, we don't care about how much complexity it actually reaches to. So yeah, so this is what we have repeated. We have a con2d layer, we have a LR layer, we are using add. Again, we have a con2d layer, we have a LR layer, again we are using add. And in the end, we are adding again that huge leap that we have discussed in SRGAN.
Inception flashback.
Yes. So the X for this con2d output is getting added to all the way to this.
Right.
So now this is put into a loop. We are looping it, we are looping it, we are looping it. And again, once we get out of the loop, we have the con2d layer and the big leap again. This layer is added all the way back to this XN. So yeah, lots of inception happening. And the next part is similar to what we had done in the SRGAN. We are using the con2d, the depth to space function, which I had explained, the channel getting less, but spatially it's increasing, the LR function, and this is repeated again. The final con2d layer using the tanh activation, then we rescale it accordingly to -1 from -1 to 1 to 0 to 255 here. And our generator is ready. So we initialize an object and return it. That's the generator done. Moving on to the discriminator. We have feature maps as the argument, leaky alpha, and the number of discriminator blocks. So this is this is as similar as it could be from
Right.
with the SRGAN.
Not much changes.
Not much changes, no. So just like you can just utilize the SRGAN from the SRGAN discriminator as well. It won't really matter that much. So the next change that does come across here is in the ESRGAN training.py, which we again have created a class for. The initialization
and the relativistic
function.
class, right? That is
Exactly.
the crux of the entire thing.
Exactly. So I'm just going to skip to the relativistic class because the rest of it is the same as SRGAN. So do not worry. Okay. Unpack the images in the train step. Get your generate your super resolution fake images. Make your meatless sandwich. Make your labels. So yeah. Now we initialize the gradient tape. So we get the predictions from the discriminator. So we split the predictions according to which of them are corresponding to the fake super resolution images, and which of them are corresponding to the real images. So here we are actually just indexing them out. So nothing fancy. We're just indexing them. Here is where we apply the relativistic error. So fake prediction becomes sigmoid of raw fake minus reduce mean raw real. So if you could have the slide on again, Ritik, if it's not a problem.
Sure. I think
is this the one that you?
Up.
Yeah, it's pulled up.
Can you go to the relativistic loss one?
Sure.
Yeah. So this part is just getting repeated in the code. So we'll just get back to the code and show them what it is.
Great, we'll do that.
Yeah, it's visible, right?
Yep.
Yes.
Yeah. So this is where we are getting we are just repeating those two equations. That is all that's happening. So if you are scared about encountering math in some research paper that you come across, do not worry, because everything can be coded. It's just numbers in the end. So yeah, that's how the discriminator is getting trained here. And again, the fun part was the generator that kind of remains the same, except for here we are also utilizing the relativistic we are calculating the relativistic loss while training the generator also. So those are the only changes that kind of pop up in ESRGAN. So but those are enough to kind of make a change. But if you really want to see what they do, I would say Aurithro, take over and show them the inference.
Yep. I have it on my screen as soon as Ritik pulls it up.
Sure.
So just yeah, it is. So just as
can I just zoom in a bit?
Of course. Is that okay?
Yes, perfect.
Cool. So just as a pointer to all my audience who have been here through the entire code walkthrough. That was diligently done by Dev, so kudos to Dev about that. I just wanted to mention that we are not going to cover the entire training process because, as I said, it's very like GANs are terribly tough to be trained and stabilized. So what we do is in our code zips and in our collab notebook that we do, we are going to infer on some pre-trained models, and we are also going to give the pre-trained models in our code zips. So look out for the code zips and the collab notebooks right after the session. And I've also run the entire collab notebook because the collab notebook takes 5 to 10 minutes, and I'm not going to waste any time. So that is how you download the code zip. You go into how they've said, like how you process the entire low resolution image and the high resolution image, create the data set, create serialized examples, prepare TF records, and
I
all
think
that.
somehow the Zoom got back.
Oh, so do you want me to zoom it again?
Yeah.
Yeah,
Is that okay?
yeah, perfect.
Okay. I'm so sorry to everyone out there. Just some noob mistakes on first live session. So this handles the entire generating TF datasets, TF records, pipelines. I'm just going to fold them as we go ahead and keep it as compact as possible. And then we move on to downloading the TF div2k dataset that we have already covered. And how do we download it? We download it with a TFDS, that is TensorFlow datasets. We do that. We also prepare the TF records as we go ahead. So that is done. Now we perform the inference on super resolution GAN. So as we already know that we are going to cover distributed setups. So with distributed setups, we either go for TPUs or GPUs due to the fact that Colab has a TPU, but we don't want to use the TPU right now. We'll use one GPU that Colab presents us with. We initialize the mirrored strategy, that is a distribution setup strategy. If you want to know more about mirrored strategy, if you don't want to know more about clustered strategies and all that stuff, I have a blog post on PyImageSearch which talks about GPUs and TPUs and distributions. So you can go ahead and look into it. Other than that, we set up the paths for the datasets which we want to ingest and infer on. So that is done. And moving on, we now load the dataset. We iterate on the dataset, like iterate on the dataset and take one batch, and then load the models. Now, as you might have remembered, that we are warming up our generator once and then fine tuning the generator again. So this pre-trained generator is the warmed up generator, and generator path is the model that has been fine tuned with along with the discriminator, right? So we have two models that we are going to perform our inference on. Now we do a bunch of matplotlib magic, and we see a good enough result on our pre-trained model. So this is a low resolution image. I hope it's quite evident, right? The SRGAN
Yes.
is eventually making sense. So the low resolution image is all pixelated. We don't want to see that. SRGAN pre-trained is good, warmed up like an athlete. And SRGAN, that is the fine-tuned, has features. It has artifacts as well, which are going to be combated in an enhanced SRGAN, but we will be okay with all the artifacts that we have. But the features are good enough, and nothing beats the high resolution image, because as we have already told, that SRGAN creates real like images, not the real images. So it's always going to be a trade-off there. And now I'll move quickly to ESRGAN inference, where everything that we do is very similar to SRGANs. So I'm just going to quickly scroll down and go into the inferenced images. Can you see that ESRGANs have lesser artifacts than SRGANs? That makes a
Yes.
huge difference. So let's recap. We had SRGANs, we had ESRGANs. What does ESRGAN do? It enhances the super resolution. How does it do that? It's quite evident that the artifacts here present in SRGAN's inference is very well combated by ESRGANs. So that kind of ends our entire wrapping around of our head for GANs, super resolution GANs, enhanced super resolution GANs. And I would like Ritvik to take over with his slides as we did the inference. I think Ritvik is on mute.
Ritvik, you're on mute.
Great.
Yep.
Thanks for the catch. And sorry for the 2 seconds over there, guys. So that brings us to the end of the live tutorial. And as we trace back our steps, we have actually covered a lot of ground. We went through a little primer on GANs and the loss function of GANs with Orithro, and they've talked us through performing super resolution with SRGANs and ESRGANs. We also went through the code. So if you're still here, give yourself a pat on the back, because that is a serious amount of knowledge for one day, and not even a day, it's like under 2 hours. So kudos to you. But we still have this one little thing that we have left to do. And any guesses what that might be?
Where is the code, Ritvik? Where is the code?
A Tesla for everyone?
No, we are not doing a Tesla today, Dev. But yeah, talking about code. So we did these throughout the session, that if you want to talk about the availability of codes and code zips, do stick around. So all of this code, collab notebooks and everything, they should be available to our PyImageSearch University members, right? And for others, as we mentioned in the beginning of the session, we are offering a 25% discount on our most comprehensive product, which includes all our books and courses. So here are the books that we have worked on, like some of them. And we have deep learning for computer vision with Python. So if you have some experience with Python and programming in general and want to get started with deep learning and computer vision, or you're a beginner in computer vision and deep learning, then this book is applicable to you. We also have OCR. So OCR text data is all around us. It is running the world, but not all of it is readable and understandable by a computer. A lot of industries are working in OCR and text detection from images. So we have got you covered there as well. And we also have books on computer vision on embedded devices like Raspberry Pi and even autonomous drones. So if you think learning, deep learning and computer vision and ensuring your career is something that you are interested in, then scan the QR code and avail the 25% discount, which is meant exclusively for you guys. And we have seen students whose lives have completely changed because of going through our content. But in our experience, the best students are the most decisive ones. So if you feel like this is the right path for you, don't sleep on this, because this, as I mentioned, this offer is only valid for a couple of hours more, because it's meant exclusively for the people who are in this live session, and it won't be here a day after or the next week. And we also encounter these questions from the students who are on the fence. And let me share a story with you. A couple of days back, we did an interview with a former student of ours whose life changed 180 degrees. And he launched his own freelancing business and runs a team of machine learning engineers just by doing our courses. And about not having enough time, just putting in 15 to 20 minutes every day will result in you being in a completely different space in a matter of 3 to 4 months. Again, his words, not mine. The person I'm talking about has changed his life, launched his own business, lost 20 kilograms and got fit. And if that feels like a goal worth pursuing, then you have your answer. And also the interview will be posted on our YouTube channel on Monday. So you won't have to take my word for it. You can just hear about it from him. And also, if you ever feel like that one of the courses that you have purchased is not working out for you, then we have a 30-day money-back guarantee, and you can avail that as well. And if you do feel like books and courses, like all our books and courses that will ensure you in your deep learning and computer vision career is something that you cannot afford right now, we also have the same discount on PyImageSearch University, which has all our OpenCV computer vision and deep learning courses on all latest topics and is growing every week. So we have tutorials on research papers and cutting edge technology coming out every week. This will include code zips, collab notebooks, and full-length videos explaining topics such as SRGAN and ESRGAN that you saw today. And trust me, guys, if you can, and if you are a beginner in deep learning and computer vision, do take this. This will take you on a long and quite productive road to learning deep learning. And consistency is the key. If you keep showing up every day in a matter of 3 to 4 months, or even like 1 or 2 months, you will be able to attain substantial knowledge and change that one thing that you need to do. And if you can't, and if you want to take something priced at a little bit lower tier, then PyImageSearch University is for you. And another thing, there's a little hack. So this 25% discount code is a secret hack, but you can apply this to any of our products and it will give you a 25% off. But again, as I said, it is only good for a couple of hours more, which means if you come back to check out on Monday or next week and apply this code, it won't work. We don't want you to stop learning at this live lesson, and we don't want you to stop thinking about GANs or SRGANs or all the brilliant ideas that you had about detecting lung cancer or satellite images. We don't want you to stop here or stop at the comment section. Go ahead, use that QR code, avail that discount, make use of the courses and the resources that we have, and someday we might just have a live lesson about the paper that you wrote.
Right.
And also, really important, guys, if you did make a purchase or you're planning to make a purchase, right after this session, do scan this QR code. And if you do, you will be able to get all of the code, the collab, the slides, everything, all of the resources used here. You will be able to attain all of that if you scan this QR code, and and those will be delivered to your inbox. So again, the people who were asking us about whether the code will be made available, whether we'll have the slides made available or not, you can have them. Just make sure that if you have made a purchase and if you have taken that first and very important step to level up your career, you do scan this QR code and you get the resources that you needed. And that is it. So Orithro, I would turn it over to you if we have any questions at this point from the audience.
Just like something to add on to Ritvik. If you are still not convinced, you can obviously, all our blogs are, you can check out the blogs, and that you can just like go through them and see if it's worth it to get our products.
Let's be honest here. We know that our products work. It's just out there. It's just out there. I know what they've meant by saying that we have our blog posts public. We get tons and tons of emails every day that we need to, sort and see how we impact a person's life. And
Right.
what we want to also advocate is that these books, the courses that we do very diligently, like the way Devjyoti very diligently went into the code walkthrough, that also includes all of us. So you will be directly in contact with whoever wrote the blog post. You can ask, suggest, even let us know that we have made a mistake, because we are humans. We are capable of doing that. And also
That's how we get better, loss
exactly,
function.
the neural network. Yeah, I was waiting for that. So so about the interview that Ritvik has also mentioned, I have seen the interview and I have been very motivated from seeing that interview, because I know that I have been able to impact on somebody's life, so much so that he is now doing good at his job. And even so much so that he now leads a team of maybe 8 or 10 people and doing AI, computer vision, and all that. And I'm really happy to advocate the courses of PyImageSearch, because we just know that it works. It just depends on you how decisive you are to purchase our code, to purchase our courses, to purchase our books, and just start. So
Yes, and show up every day. That's
yeah,
the key.
yeah, that's the key.
Determination is the
Start,
key.
Even
start,
if it's
and be
like for
disciplined.
10 minutes, that's all you have a day. Do it, dedicate it to learning,
Mhm.
even if it's learning from our tutorials and from our blogs, and it will change the way you perceive this field.
And just to be very clear about it, we have a 30 days money back.
Yes.
So no risk, no risk at all.
Uh,
So that's about it from our
uh,
side. We I saw a lot of questions which were handled by Devjyoti right in the comments. So Devjyoti, kudos to that. I am also going to keep an eye out for a minute or two from people who would want to ask us something from from the live lesson, something about SRGAN, CSRGANs, GANs, or whatever. And do let us know how the live lesson went.
yeah.
Do you
And
feel
to the
Mhm.
170 people who stuck around till the end, you have our thanks.
Yeah, yeah. We do. We do.
More than
We
that,
thank you.
you learned about two very complicated architectures of GANs in a matter of 2 hours, which is like recommendable. I mean,
Yeah.
you really did achieve something. So
Good. I think it's about them acknowledging our presence, and I really like that. So we could maybe sign off, Ritvik, Dev.
Yeah. Thank you,
just
people.
just to make sure, yes, before we sign off, if
Mhm.
anyone is out there and thinking about this, couple of hours, that's all you have. And
Mhm.
because we know that people who are decisive are going to take up on this opportunity and go into these courses. This is everything that we have made, all of our courses and books, that there's a flat 25% off on it. Again, if that's not for you and that's something that you need to reconsider right at this moment, you always have university, which comes at a very much less tier price, and you also have the discount code which is applicable everywhere on the all the checkout pages. Again, if you have made a purchase, please scan this QR code, because that will enable us to deliver you these code, collab, and resources that we have used in this live learning session. Okay, all I see is people acknowledging our presence. So yeah, thank you guys for sticking around, and it has been great talking to you.